Okay. Well, good morning, everyone, and thank you all for coming early today to attend our workshop on applied longitudinal data analysis. We have a distinguished workshop speaker today, and I'm very happy to introduce him. Professor Garrett Fitzmaurice is Professor of Biostatistics at the Harvard T.H. Chan School of Public Health, where he has been for most of his academic career since completing his Doctor of Science at the same institution in 1993. Professor Fitzmaurice has written, with two of his colleagues at Harvard, the best-selling textbook Applied Longitudinal Data Analysis, about which he has delivered numerous well-received workshops for statisticians, epidemiologists, biostatisticians, and other researchers at various meetings, including the joint statistical meetings. He's among the editors of Longitudinal Data Analysis and Handbook of Missing Data, which are part of Chapman and Hall's series of handbooks on modern statistical methods. He is a fellow of the American Statistical Association. Although I haven't met Garrett in person before today, his work has played a big role in my own education and training as a statistician. His seminal papers in the early 90s on mixed data analysis were the reason I got into it, which I'm still happily pursuing to this day. So please welcome Professor Garrett Fitzmaurice.
Thank you. Well, thank you very much, Alex, for that very nice introduction. Karen, I want to thank you very much for organizing this meeting and inviting me. And before I forget, Mariko, thank you for doing all of the arrangements. You're super. As Alex mentioned, longitudinal data analysis has really sort of been a topic of both my research and teaching interests, I think now for about the past 20 years or so. And so I was really delighted when Karen invited me to give this workshop. I've been teaching courses on longitudinal data analysis for many years. I teach a semester-long course at the Harvard School of Public Health, but I also teach various short courses, week-long courses at summer schools, 1 to 3 day courses, and workshops much like today. As Alex mentioned, I've given a 1 day course on longitudinal data analysis at the joint statistical meetings for a number of years, and today's presentation will be relatively similar to that. So if you already attended my course at the joint statistical meetings, you can go home and make the best of your Saturday, because there will be a large degree of overlap. Now, I mentioned the course, the semester-long course that I teach at the Harvard School of Public Health for two reasons. One is when we teach our graduate students at the Harvard School of Public Health in a semester-long course, that's a course that meets for 16 weeks, twice a week, 2-hour lectures twice a week. So we have about 60 plus hours to really cover the topic. Today we have a fraction of that time, probably a little bit less than 6 hours. So my goal is not to compress a semester-long course into a day. That would not go down too well with most of you. Instead, what I really want to do is just sort of hit some of the key points in the analysis of longitudinal data. So there's going to really be a lot of emphasis on important fundamental concepts and a little bit less attention to technical details and so on. The other reason I mentioned the course that I teach at the Harvard School of Public Health is because the course was developed by a good colleague of mine, Nan Laird, about 25 years ago. We had taught a course to our doctoral students in biostatistics, but many of the doctoral students at the School of Public Health in epidemiology, environmental health, nutrition, and various other disciplines were conducting many important prospective longitudinal studies and really needed to have an understanding of the statistical methods for their analysis. And so Nan very wisely decided to devise a course for these students. So it's really a course primarily aimed at doctoral level students, mainly outside of biostatistics. The course that Nan devised was very successful. Subsequently, another colleague of mine, Jim Ware, who sadly passed away last April, he started teaching that course. And then when I joined the faculty, I took the course over. And after Nan and Jim and I had probably had about 6 or 7 years experience teaching the course, we decided to write a textbook that was really a companion to the course. Because at the time, at least, many of the textbooks on longitudinal data analysis were just maybe a little bit too technical for the audience that we were pitching the course at. So throughout today, as I said, I'm really not going to get into a lot of details, but at the end of each session, I will refer you to various chapters in our textbook where if you have an interest and want to sort of follow up on any of the topics that I'm covering, you may find some additional information. And so I have a copy of the book if anybody wants to have a browse through it anytime during the day. And so I have to apologize in advance for the shameless self-promotion. Because I've written a book on the topic and I teach from it, it's very easy for me to just refer to various chapters. I'll try to also point you to some other references. Also, in this age of full disclosure, I should tell you as a co-author on a textbook, I do receive a royalty check from John Wiley & Sons. But I can also disclose that that check that I received from John Wiley & Sons has no impact on my children's dental bills. So I'm not trying to sell you a textbook. It really has very little financial implications for me. Okay. So this is sort of more or less the organization for the lectures today. So I'm going to start off in the first session really with some very fundamental and basic concepts and try to provide a little bit of motivation with a couple of examples. And I suspect in this room there's a whole variety of different levels of familiarity with longitudinal data analysis. And for those of you who are already very familiar with longitudinal studies and some of the methods for their analysis, I would ask you to sort of bear with me in the first session. I just want to really make sure that everybody is on the same page as we proceed through the remaining sessions today. So we'll begin fairly slowly. It'll allow that caffeine to kick in. And I'll talk about some basic concepts, introduce some examples to really sort of solidify some of the ideas. Then in the second session, I'm going to talk about a very versatile and useful class of models for the analysis of longitudinal data when the outcome variable is continuous or quantitative, so-called linear mixed effects models. And then in the afternoon session, the first session in the afternoon, I'm going to talk about ways to try to make linear mixed effects models just a little bit more flexible for the analysis of longitudinal data by introducing the ideas of sort of smoothing or semi-parametric regressions, because there's some nice connections between a particular type of smoothing, penalized splines, and linear mixed effects models. And so you can sort of marry the two together quite easily to make your longitudinal analysis just a little bit more flexible. And then the final session is going to be focusing not on continuous outcomes, but on categorical or discrete data. So we may have repeated measurements of a binary outcome denoting success or failure defined in some fashion, measured repeatedly over time, or we may have repeated measurements of a count, perhaps counts of the number of symptoms an individual is experiencing, and so on. So the final session really is going to be talking about generalized linear models and their extension to the longitudinal data setting. And so I'm going to sort of emphasize probably two of the most widely used classes of models, so-called marginal models and generalized linear mixed effects models. So that should sort of more or less bring us to the end of the day. So I believe I've got the times right here for the sessions. So the first session will run from about 9 o'clock, which is about right, to 10:15. Then there'll be a break, and then the second session from 10:30 to 12. And then we'll have a lunch break and start up again at 1:15. I'm putting up these times because one thing I'm terrible at is managing time. So I'm depending upon you to at least give me nonverbal signs if I'm going over the anticipated breaks, okay? So your first break you should anticipate around about 10:15. Don't start to remind me at about 11:15 that I should have taken a break, okay? The second thing I just want to mention is I'm very happy to take questions at any point during the sessions. So if there's anything that seems confusing or you just have a question about something, please interrupt at any point at all during the sessions. It is a large group. If the questions start coming a little bit too fast and too many that I won't actually get through the material, I may have to defer answering some of them to maybe during the breaks. Okay? All right, so in this first session, I really want to sort of focus on basic concepts. And I just want to sort of begin by mentioning that statistical methods for the analysis of longitudinal data has really been a topic of great interest to statisticians really now for the past 25 years or so. And there actually have been quite remarkable advances in methods. And fortunately also these methods are now currently available in almost every statistical software package or routines that you may want to use. Now, for the setting where your outcome variable of interest is quantitative or continuous, we can extend familiar linear regression models to handle longitudinal data of such an outcome, and in a sense, extend familiar linear regression so it can handle the correlation amongst repeated measures over time. And by and large, for linear models, the correlation amongst the repeated measurements is often handled in one of two different ways. One is to very explicitly model the correlation, or in particular the covariance. We'll talk a little bit about covariance later. Or the other way is implicitly via the introduction of random effects. And so it's the latter, accounting for correlation or covariation through the introduction of random effects, that leads to this very useful class of models, linear mixed effects models. That'll be the focus of the second session and also the third. So let me just begin with talking about some basic concepts. And again, apologies in advance to anybody if this is very, very familiar territory. I just want to make sure that the jargon and the terminology that I'm using is at least familiar to everyone from the outset. So the defining feature of a longitudinal study is simply repeated measurements on the same individuals over time. So the lowest common denominator would be 2 repeated measurements, but typically we would have 3 or more. And because we take repeated measurements on the same individual over time, and each individual acts as his or her own control, longitudinal studies allow a very direct way to study change over time. And so the real rationale for conducting a longitudinal study, and the main goal of most longitudinal studies, is to characterize change in some outcome variable of interest over time. But not only are we just interested in change per se, but we're also usually very interested in what are the factors that may have an influence on change. And so those factors, they could be a treatment intervention. You may have randomized one group of individuals to a new intervention and another to the standard, and you want to know, does treatment have an effect on change over time? Does the new intervention lead to greater improvements in the outcome over time? Or it may be that you have exposures, smokers and non-smokers, and you're interested in whether smoking has an influence on lung function growth over time, okay? Or lung function decline over time if you get to my age. Or it could be some characteristic of individuals. It could be biologic sex or socioeconomic status. So in most longitudinal studies, the real reason for doing a longitudinal study is so you can directly measure change, but ordinarily we're also interested in what are the factors that have an influence on change. Now, the main complicating feature of longitudinal analysis, the reason why we often have to have courses and books and workshops like today on the analysis of longitudinal data is because there's two aspects of the data that complicate the analysis. That means we can't use a lot of the routine regression techniques we may already be familiar with. And the first feature, I think, is well known and well recognized, and that is that if you take repeated measurements on the same individuals over time, those repeated measurements will be correlated, and they'll be positively correlated. So if you know that my systolic blood pressure is high today, then you actually have a lot of information about future measures of my systolic blood pressure. You have information about the likely values of my systolic blood pressure not only tomorrow, 6 months from now, a year from now, in fact, even 10, 15, 20 years from now. So repeated measurements on the same individual over time are not independent observations, they're positively correlated. And I think that feature is well recognized by most people when they think about a longitudinal study. The second feature is often not quite so widely appreciated, and that is when you take repeated measurements over time, the variability of those measures is often heterogeneous over time, in the sense that the amount of variability that you see in that outcome at the start of your longitudinal study can often be quite different than the amount of variability that you see in the outcome by the close of follow-up. Okay? And so it's really both of those aspects that complicate the analysis. And when we put both of those aspects together, correlation and variability, that's really what we mean by covariation. And so the variance-covariance matrix plays an important role in longitudinal analysis. Okay, just a little bit of terminology and jargon, again, just to make sure that everybody understands what I mean. So I'm going to refer to the individuals as subjects in most of these applications, and that just simply means the participants in the longitudinal study. They're not necessarily human subjects. In a veterinary example, they could be cats or dogs or cattle. They could be hospitals or other units. Okay, so I'm basically going to refer to the unit of analysis as the individual or subject. Okay, and I think that's pretty familiar. I'll also use the term occasions a lot, and so in a longitudinal study, individuals are measured repeatedly at different occasions. But we're going to quickly see that the notion of occasions only really applies in a fairly restricted set of settings. And so instead, what we'll often have to talk about are the times of the repeated measurements rather than occasions. And we can't always use those two terms interchangeably. And we'll see when we can and when we can't. The other thing is, in many different longitudinal studies, both the number of repeated measurements and their timing can vary quite widely from one study to another. So some longitudinal studies are for a relatively short duration and may only have a relatively small number of repeated measurements. There's often quite large longitudinal studies that are ongoing and have been conducted over 15, 20 years. Okay? So different longitudinal studies will have different numbers of repeated measurements. Their timing can vary quite widely. But when we consider a particular longitudinal study, when the number and timing of the repeated measurements are the same for each participant in that study, I'm going to refer to such a study design as being balanced over time. So what I mean by balanced is, in a longitudinal study, each individual is measured the same number of times and at the same set of times. Okay? Otherwise, the study design is unbalanced or has some degree of imbalance. Now, this idea of balance is really probably only of sort of historical importance, because a lot of the initial methods that were used for the analysis of longitudinal data required that your data were balanced. Okay? To be useful, most modern methods for longitudinal analysis need to be able to handle imbalance, because even if you design a study such that it's balanced, what you'll actually collect will often be very imbalanced. Okay? But If you have a longitudinal study that's balanced, it does greatly simplify things in a variety of ways, and we'll see that in the example in a second. Okay? So any questions about the terminology? Okay, good. So I want to introduce two examples, and these two examples are almost sort of like opposite ends of the rainbow. So the first example is, what could be referred to as a very carefully controlled longitudinal experiment, a longitudinal clinical trial. So this first example comes from a study known as the Treatment of Lead-Exposed Children's Trial. As many of you know, exposure to lead during infancy is associated with all sorts of cognitive deficits. And so any of you who have a young infant will know that when you make a visit to the pediatrician, they very often will take the finger and take a blood sample from a pinprick, send it off to the laboratory to check for blood lead levels. Okay? Now, most of the exposure to lead tends to be from deteriorating paint in older homes. So at least in the US, and I suspect in Canada, if not earlier in Canada, lead used to be used as both a pigment and drying agent in oil-based paints, and in the US, at least in 1978, it was banned. But if you have an older home that was built before the late 70s, there was probably a good chance that there's some lead-based paint in the home. And then what happens is, as that paint deteriorates and flakes, small paint chips end up on the floor, and then your little rug rat who's crawling around, the minute it finds a flake, where does it go? Straight into the mouth. And that's the typical route of exposure to lead for young infants. Now, fortunately, if an infant is exposed to lead, there are chelation therapies for removing the lead from the body. And at the time of this clinical trial, the standard chelation therapy had two features that made it somewhat unappealing for very young infants. First of all, it required hospitalization, okay, which is very expensive. And secondly, it's an intravenous treatment. And so that's quite stressful for both the young infant and particularly for the parents of the infant. So the goal of this trial was to look at an oral chelating agent called Succimer that could be given on an outpatient basis. Succimer had been shown to be effective for removing lead in adults, and this was a study of young infants. And so I'm going to show you some data from this clinical trial. And so this was a randomized placebo-controlled trial where half the infants were randomized to either receive the active oral agent, Succimer, or to receive placebo. And then we have repeated measurements of blood lead level at baseline, or you can think of that as being week 0, prior to when a coin was flipped and you're randomized to either the Succimer group or placebo. And then we have follow-up measures of blood lead level at week 1, week 4, and week 6. I can see some of you frowning, saying, how in the world could you take a group of young infants who've been exposed to lead and randomize them to receive a placebo? Well, this was a trial of infants who had blood lead levels that were in a range that were considered to be of concern. So they were below, at the time, 45 micrograms per deciliter. 45 micrograms per deciliter at the time of this trial was the cutoff where if you had an infant who had blood lead levels above that, you would just automatically recommend standard chelation therapy, an overnight stay in the hospital, intravenous treatment, and so on and so forth. So these were infants who sort of fell in a gray zone. They had blood lead levels that were high enough to be of concern, but not so high that it would automatically trigger standard chelation therapy. And so it was deemed ethical to conduct such a trial. Now, this example is nice because it's an example of a balanced longitudinal design. So each child has 4 measures of blood lead level, one at week 0 or baseline, another at week 1, week 4, and week 6. So each child has 4 measures, and the timing of the measures are the same for everyone. So the notion of occasions actually makes a lot of sense, because I can talk about the first occasion of measurement, and it means the same thing for every child. It's a baseline measurement. And I can talk about the third occasion, and that means the same thing for everybody, because that's a measurement at 4 weeks. And I can talk about the final or the 4th occasion, okay? And because we have balanced data, it actually makes the analysis so much simpler, because you can do all of the simple descriptive statistics before you even think about applying any sort of a model to try to discern whether the pattern of change in blood lead levels differs in these 2 treatment arms. So without knowing anything about a longitudinal analysis, the very first thing you might do is simply calculate the mean blood lead levels in the 2 treatment groups. And so that's what's just presented here. So here we have the succimer group. So these are the 50 infants who were randomized to the active oral chelating agent succimer. Here's the mean blood lead level at baseline, about 26.5. And then you can see there's a drop in the mean to about 13.5 at week 1. And then, curiously, it starts to increase again at week 4. And by week 6, it's gone up to 20.8. We can also do the same in the placebo group. And so if you look at the means in the placebo group, you can see that at baseline it's about 26.3. It's very similar to the mean in the succimer group. And why is that? Just due to randomization. We took 100 children with measured blood lead levels, and then we simply divided them on the basis of a flip of a coin into 2 groups. And so apart from sampling variability, we would expect the means to be very similar. In the placebo group, you can see there's a small decline in blood lead levels at week 1 through 4 and week 6. Also, what I'm showing in parentheses is the standard deviation. So a measure of the variability of the repeated measurements over time. So very, very straightforward to calculate means. Very, very straightforward to calculate standard deviations. In fact, if I wanted to calculate correlation, it would also be very straightforward, and I'll show you that a little bit later. And why is that? Because it's a balanced design. Everybody's set of repeated measurements is perfectly aligned at week 0, 1, 4, and 6. Okay? Now, because time has a natural sequencing or ordering, another thing you could do is just simply plot the means. Okay, so I could just take the means from this table and create a plot of the means over time. And so here we have the means in the placebo group that declined a little bit. And then you can see a very different pattern of change in the succimer group. We see this very sharp decline and then followed by a rebound effect. So 2 things I want to mention. In addition to either being randomized to receive succimer or placebo, also both groups, the parents were provided with educational information about how to reduce exposure within the home. So these are infants who are being exposed to lead in older homes with deteriorating paint. And if you wipe down surfaces and you vacuum very carefully and so on, you can sort of minimize the future exposure. Okay? Now, this pattern here is very curious for the succimer group. There was a very sharp decline, and then we can see this is sort of a rebound effect. And so before you actually approach the analysis, because this is a balanced longitudinal design, we have all of the descriptive statistics. You already know what's happening in terms of the pattern of change. It is very different in the 2 groups, and the pattern looks quite different as well. The physicians have a good explanation for why in the succimer group the blood lead levels would first go down and then start to creep back up again. And that's because what succimer does is it helps the infant excrete lead that's in the blood. But lead is also stored in the tissue and the bones. And so what happens is when the infant excretes some of the lead that's in the blood, then the lead that's stored in the tissue and the bones becomes mobilized, and a new equilibrium for the blood lead levels is then reached. And so what this actually suggests is that you very often have to treat infants 2 or 3 or 4 times, each time trying to bring down the blood lead levels. Okay? These are data really just for one course of treatment. Okay, so that's the first example. It's a very carefully controlled study, and because of its balance, it makes it very simple. Even before you run to the computer and try to produce a longitudinal analysis, you already have an idea of what's happening. Okay?